I'm Dan Rowe, and I'll be talking about Nordic's air-to-water heat pump. That's our ATW series today. I'll try not to go into too much detail, keep the meeting a reasonable length and so on. But and I was just mentioning, as I was mentioning, I'm not a salesman. I'm an engineer, so I've done plenty of these presentations though. So if you have any technical questions, you can maybe we'll have a time at the end when you can ask them. Just a little bit about our company. Yeah, the company is actually Maritime Geothermal, and it was founded in 1983. We made geothermal heat pumps or ground source heat pumps for most of our history, and in 2014 to 15, that season, we started to make air source heat pumps as well, central air source heat pumps, and those have been a very good seller. Those are the ones I'll be talking about today. We have a very large or a very wide product line, and I'll only be talking about the air source heat pumps today. And we do all our manufacturing in Canada, which is kind of an unusual situation. Most, so-called Canadian companies are importing heat pumps from China or something like this. But this is our factory. It's where I am right now. Actually, I normally work from home, but I'm at this factory right now, and it's a 30,000 square foot facility in Petitcodiac, New Brunswick, near Moncton. These are some of the people you might run across, the main people at Maritime Geothermal. Susan Kay is our office manager, so she's taking all the orders and dealing with logistics and quotes and that sort of thing. I'm the center person here. It's probably an old picture, so I think I still look like that, but I'm the product development engineer, so my duties were originally to design all the heat pumps in 3D CAD. And of course, that's expanded, so I write all the technical documentation and also do customer support right now. And Chris Geddes is the other senior engineer at Maritime Geothermal, so he's somebody you might talk to in regards to technical support, and he's our plant and electronics and coding engineer. Coding has taken up, it's kind of overtaken his job since the product's changed over the years, so we're all quite busy. As I mentioned, we have a super wide product line. These are just a few of them. We make every variety of geothermal heat pump that you might come across. So there's some large water-to-water heat pumps pictured there. We also make water-to-air units, both for commercial and residential applications, and the air source heat pumps that I'll be talking about. So we make 3 different series of air source heat pump. Of course, the best seller is our ATW series. That's the air-to-water. It's been a little tricky to find a good air-to-water heat pump, so that's it was a really good move for our president, who still owns the company, to direct us into this field in 2015. We were all a little skeptical since we had been making geothermal heat pumps for a long time, but it's been a very good product, and since it's been out since 2015, it's also it's a kind of a proven product now. It's not something that we're just coming out with. We also make an air-to-air heat pump, and a combination, which is like a triple function air source heat pump, which can heat water for in-floor heating, as well as heat and cool through a ducted air system. So there's 3 varieties of heat pump that we make on the air source side. And we also make geothermal versions of all these heat pumps as well. A couple of upcoming series I have in gray here. It's hard to promise dates, so you're kind of always reluctant to talk about them as an engineer, but we plan to come out with a high temperature air-to-water heat pump. That's going to be our ATW series, and also an ATW2 series, which will be a dual compressor air-to-water heat pump that's going to take us up into the next size range. So for large houses or for commercial applications. So something to keep your eye out for in the future. Hopefully next year.
Can I interject with a question?
Sure.
If you can just go back to the previous slide. So the dual compressor is simply to expand the capacity. Like are there any other benefits to having that?
Yes, yeah. The 2 applications for it will be just a doubling in the available model size. So right now our largest unit is the ATW 75, which is kind of a nominal 5-ton unit. Whereas this ATW2 will go up to size 150, so it'll be about a 10-ton unit. So that you could just use it for a larger space or a larger building. But the other application will be this will have 2 compressors, so it'll have a dual speed or a dual stage compressor as well as a fixed speed compressor. So it'll be able to dial back a lot further. So you could put it in place, like you could put an ATW 150 where you would have put an ATW 75 previously, but the ATW 150 would spend most of its time running with only one compressor energized, and then on a cold day, where instead of using backup heat to make up the capacity difference due to it being harder to extract heat from the outdoor air, you could use this ATW2 150, which would have the capacity to dial up, kind of thing, in case you needed more capacity on a cold day.
Great. Okay, so you're addressing part load issues.
Yeah, exactly.
Sizing. Yeah.
I hate to the only danger to this is that it's going to make our product offering even more complicated. But for those who understand it, I think it'll be a good benefit.
Oh yeah, you might be
I guess
inviting
we're
more
all
technical.
engineers, so we will certainly understand it in this crowd.
Right. Yeah. Okay. No, it's interesting. Good to know.
Yeah. Exactly. So this is our ATW series as it stands now, and the only thing that we've changed about it over the I guess it's been 7 or 8 years it's been out is the color. I guess we've made the colors match between the indoor and outdoor units, and I've made this 4-fan outdoor unit a little bit more compact. So, but it's been the same idea all along. Just let me turn my phone down here. There we go. That's so one important thing to mention about our air to water system is that it's a split system. If you find other air to water heat pumps on the market, they're likely to be monoblocks. That's the way most people are making them. So that is a single unit which sits outside. It doesn't make sense to us for a cold climate to have your hydronic water from your in-floor system or your domestic water going into the cold to get heated. So it makes sense to us to have a split system where our compressor and electronics and refrigerant to water heat exchanger are all in the indoor unit, and the only thing in the outdoor unit are refrigerant to air heat exchanger and the fans. So this is it's hard to find a split system like this. Even other systems that appear to be split are not really split systems. They're just like an outdoor monoblock with a indoor buffer tank or something like that. So
and we got good feedback from a contractor who's worked with these who said like the serviceability, right? So like fewer components outside exposed to the weather for longevity, and then also if something goes wrong to service it, being able to service most of the components inside. He said at the temperatures that they more likely will have problems at the cold temperatures, like you can't his workers can't work in those temperatures.
For sure, yeah, exactly. So coming from the geothermal background, kind of helped us break out of the way that every air source heat pump was being made in 2014 and 15. And you'll notice some other significant differences that we hadn't been making air source heat pumps for many years, so we didn't have anything to conform to. We just tried to solve problems that we saw with air source heat pumps that were already out on the market. So there's a few more features that I'll mention here too, but the most important one being that it's a split system, I guess. Just the basics first, I guess. The ATW series can heat water for in-floor heating or other hydronic heating, chill water in the summer. Because we have a split system, we can have a desuperheater to heat domestic water. So that's a feature which uses about 5% of the unit's capacity while it's running for space heating or cooling purposes, and directs that capacity toward a domestic hot water tank through a double wall heat exchanger. Of course, it uses heat transfer from the outdoor air, so it's always exchanging heat with the outdoor air, no matter which mode it's in. The size range is 2 to 5 nominal tons. I guess we don't sell too many of the 2 or 3 ton models, especially not the 2 ton. But I guess being passive house people, you might be more interested in the lower sizes actually. And as I mentioned, it's a split rather than monoblock design.
So I tend to ask quite a few questions.
Go ahead. Yeah.
Can you go back to the previous slide? So there's 5%, just trying to understand the capacity for hot water. So so you say you're providing space heating, right? There's a call, you're heating a buffer tank, or you're sending it in floor. I don't know exactly how the kind of schematic.
Yeah, you're always heating or chilling a buffer tank. You're right there. Yeah.
Okay. Yeah. So you're then, and you've got, say it's 5-ton unit. Now you want to have a hot water. You have a call for hot water. You need to heat the hot water tank.
So yeah, it's not call based for sure. So it's not an on-demand domestic water heating device. What it does is while the compressor is running for space heating or cooling, the hot gas from the compressor is always going through a double wall heat exchanger that's connected to the domestic water preheat tank. And there's a built-in circulator that circulates water through there. So it can heat domestic. If there's, let's say your heat pump is running and there's no domestic water demand, it's going to heat that preheat tank right up to 140. And that's something that's good about the desuperheater feature is that it's not limited to the condensing temperature because it's using a little bit of heat off the hot gas before that gas hits the condenser. So it can commonly heat the domestic water right up to the plumbing flow temperature of 60 degrees Celsius or 140 Fahrenheit, whereas the main output is limited to 105 to 120, which I'll mention in a bit here. But it doesn't heat domestic water on domestic water demand kind of thing. So you do need a final heating device to do the rest of the job in case the desuperheater isn't running enough hours to give you all your hot water kind of thing.
So I'm just trying to understand that it's a byproduct. I don't know if that's the right word, but it's when it's in heating or cooling mode that you've got the desuperheater basically collecting energy into a separate tank that you
domestic water tank, yeah.
Water.
So that's like separate from the buffer tank. So the buffer tank contains the closed loop, like in-floor heating water. And then this desuperheater is connected to a totally different circuit, which only has potable water in it. It's the preheat tank is usually just a 40-gallon. Doesn't have to be anything special about it. The elements aren't even hooked up, but the least expensive kind of tank to get is just used to be a $400 tank from Home Depot. It's probably more these days, but so the desuperheater does what it can. Yeah, it might heat the water up all the way, but it might only get it up to a lower temperature than what you require for the house. So then a final heating device will take water from that preheat tank and heat it the rest of the way if needed.
Okay, but it's
electric tank. Yeah.
Right. Another tank. Yeah. Okay. So you have a 40-gallon, but especially if you're in like a multi-family setting or whatever, you probably need to bring that into another
60-gallon or whatever kind of final water heater they would have anyway, kind of thing. So it could be an instantaneous heater, even the final heater. But for a preheat tank, I would normally just choose a 40-gallon electric water heater without the elements hooked up.
Okay, so that's basically the interface between this system and your hot water system, essentially.
Right, and if the one more thing to mention there is that if the domestic water gets all the way to 140, there's a temperature switch to turn off the circulation pump that's built into the desuperheater in the heat pump, so it'll stop heating water at in practice up to maybe 145, 140, 145, something like this Fahrenheit.
Okay, and this is all just taking about 5% of the capacity of the system to do this. Okay.
Yeah, and it's in heating mode, you're getting the same COP heating domestic water as the main output, of course, and in cooling mode, you're actually taking heat out of the space and putting it in the domestic water tank, so that's free. So whatever it does in during heating mode, whatever water heating it does is actually heat that's been removed from your living space. So it's kind of neat.
Your living space. Well, yeah, okay, because if you're like in a home and this is a mechanical room, that's what you mean. Because
if you're in cooling mode, you're removing heat from the. I don't know if you do too much cooling in your house designs, but if you do any hydronic cooling, then you're removing heat from the space and normally rejecting it to the outdoor air. But in this case, you're rejecting part of it to the domestic water tank, which is.
Yeah, so that's where I was being clear. Maybe I just misheard you. So yeah, because you should be, and you are rejecting heat to the outside, but instead of rejecting it all, you're just diverting some of that into the hot water.
Exactly.
Preheat.
Yeah. It's too bad you couldn't direct it all into the domestic water, but that's just the nature of the desuperheater. It's kind of it's a standard feature, and it's not an optional add-on or something like that. And it's quite it's simple and cost effective to have that feature. So it's a good one to have. Appreciate it. Yeah.
And then what does obviously it depends on the load. I'm just wondering, like, okay, so let's just stick with homes because these are often installed in homes. Like, what percentage your hot water load is such a system typically, so not peak, but just kind of if you looked at
Yeah.
annually how
As a
much it
rule of
would
thumb,
cover?
like in the say in the middle of the winter when, well, especially an air source heat pump is certainly running all day when it's you know, in the middle of winter when it's fairly cold out. So during those kind of conditions, as a rule of thumb, it might do all the heat all the domestic water for a typical household. And then in shoulder seasons, it'll do some fraction, and in the summer, depending on how much cooling you're doing, it'll do whatever that a corresponding fraction of the domestic water load. If it's running all summer, it'll be similar to the winter too, but quite often the cooling load is quite a bit less. I guess if you're talking about lower capacities, like if you're looking for at small model sizes for passive houses, that would be something to take into account, because I guess people who live in a passive house aren't necessarily using correspondingly less hot water. So it might that rule of thumb might not really hold up if you only have a 2-ton heat pump and you have a you know, due to there not being a very high cooling and heating load, but you would have the same domestic water load as perhaps as a regular house. So maybe it wouldn't do all the heating in your case, domestic water heating for a typical household in the middle of winter. But that's the
Yeah,
traditional rule of thumb anyway. So
exactly. Yeah, you're kind of getting into something I was thinking about, like, well, how much could you get out? And that's right. With passivhaus, we have
it
overall
might be a little bit of
district heating.
actually for your application, thinking about it, it might be a little bit less of an important feature, because with a small heat pump, it's gonna have a correspondingly smaller domestic water heating capacity, right, through the desuperheater. But you would have
True.
it.
Yeah, that's kind of my instinct here. Like in the summertime, we might want to be able to switch it over and do as much preheat as we can, and then, in other words, switch it to heating mode, do as much domestic hot water heating as we can, and then top it up.
Yeah, you can do dedicated domestic water preheating just with a heating zone. So that would be like a tank with a coil in it most of the time, like an indirect tank. What that doesn't have that the desuperheater does is that it's limited to below the main output temperature, right? So you would certainly need it would heat domestic water on demand, but not right up to 140 degrees Fahrenheit or 60 degrees Celsius.
So you can't, because you have a buffer tank for cooling as well, I presume?
Well, there's different ways you can do it. Most installations just use one buffer tank, and they do a seasonal switchover.
Gotcha. Okay.
So from cooling to heating, and you would do that by providing the heat pump a dry contact R to O, so an O signal basically. So that'd be usually done by a zone controller or something like that. But there is a built-in function in the control board, which I'll show you in a minute, that has the functionality to switch back and forth automatically and heat one tank and cool another tank. So that would be useful in case you have space for all these tanks, of course. And also if you want to do dedicated domestic water preheating all summer, because if you chill your main buffer tank, you don't have any hot water heated in order to do domestic water preheating.
Well, so I guess the question is, are you using the waste heat from the cooling, or are you just switching out of cooling mode and now you're in heating mode, but you're doing hot water?
No, you're limited to exchanging heat with the outdoor air for the main cooling and heating functions of the heat pump. So with the dedicated domestic water preheating, you're actually switching the heat pump into cooling mode, and it has control for a 3-way valve to direct the main outputs to the cooling tank, and then you're cooling that tank until it reaches its set point, and then checking the hot tank and seeing if that needs to be heated. Maybe because someone's had some, doing the dishes or had a shower or whatever.
Gotcha.
So
okay.
it is switching back and forth, and you can set the priority. You can, have it do the cooling. If there's simultaneous demands, you can have it do the cooling first or the heating first.
Okay, but it's not a waste heat process. Like you're still
exactly.
rejecting the. Yeah. Okay.
Yeah. Air source heat pumps aren't as flexible as water to water heat pumps. With water to water heat pumps, you can. It is more complicated, but you can do simultaneous heating and cooling with a water to water heat pump, and that's something that we're also can give advice on. Maybe not. Might not be a part of this presentation, but in the manuals we have for both the series, or for all of our series, have lots of piping diagrams with simultaneous heating and cooling and this sort of thing. Certainly in the ATW manual, which I'll show you where to find, there are diagrams for the 2 buffer tanks and a single buffer tank. Also, like putting a boiler in parallel with the heat pump. So it's good to have these recommended diagrams, because that if you follow these diagrams, you know it's going to work. And there's lots of other ways to do it, but then you're kind of, if it doesn't work, you're kind of on your own there. So yeah, lots of different ways to do things for sure.
Well, and then a couple of related questions then. On that, then, if you wanted to scale to multifamily, I presume you could, put these in series or parallel. I don't know what the setup, but you can you like just scale them like that easily? So if you had like
any kind of hydronic heat pump, like a water-to-water heat pump or an air-to-water heat pump, is very easy to put multiple units in parallel to satisfy larger loads than you would be able to satisfy with just a single unit. In the air-to-water case, it tops out at 5 tons in capacity. So for larger houses will often require more than that. So we've had up to there was just a project come in where actually this is a picture of one of the warehouses, but there's some net zero warehouses in Halifax, and they just specified 10 ATWs for the same warehouse. So it's very, I mean, that's quite a few, but it's easy to put multiple units in parallel to satisfy larger loads. And
yeah, I was going to ask you guys what your biggest installed. Sorry about that. What your biggest installed installation was?
Yeah. So that's just recent. Not many. This is an engineer who's experienced. He'd done a bunch of these warehouses with. I think the first warehouses had 6 units each. And then he did some smaller warehouses that had 4 units each, and now he's doing a warehouse that has 10 units. And that's the most units I've heard of on the air-to-water side. That's a lot of piping. But he really likes units, and
sure.
He likes the way they run. They're only heating water to like 80 degrees or something like that, so they're super efficient, and they worked out really well in that application. So. Another reason to put multiple units where even if there was a larger model size heat pump, if you only have single phase electrical power, then you'd be limited to the largest single phase model, which is going to be the existing ATW 75, like that 5 ton. There wouldn't be a single phase compressor that would be suitable for a larger model size. So single phase, usually houses only have single phase electrical power, so you'd only be using an ATW 75 anyway. The ATW2 that I mentioned earlier has 2 smaller compressors in it, so that might also be available in single phase. But in general, that's something to be aware of anyway.
Okay, and then I don't know if somebody else had a question. No? Oh, maybe that was just an echo. Okay. The hot water. So one potential strategy for passives, they're very inertial, as you can imagine, right? They don't change quickly with the outside temperature, the indoor temperature. So one strategy is actually to run a system at a lower capacity, but especially if you have a buffer tank, you're going to have a steadier draw. You're not going to have as peaky of a draw from that tank. Yeah. So I'm wondering if you actually had a smaller capacity heat pump that's running more regularly, maybe continuously throughout the day for a bunch of the winter, you could get more hot water capacity, domestic hot water output out of that strategy. Could you?
Maybe. The thing with air source heat pumps is that in practice, like they're as it gets colder outside, this is unlike a geothermal heat pump, but as it gets colder outside, the COP and the capacity of the heat pump go down and your heat load goes up. So for an average house, it's expected that backup heat or auxiliary heat will be running alongside the heat pump in order to satisfy the load, and the heat pump's going to be running all day when it's reasonably cold out already. So you don't have a lot of extra capacity to keep it on and heat an enormous tank of water in order to have thermal storage. Because in practice, air source heat pumps are like running all the time when it's cold out anyway, just because of their reduced capacity when.
Sorry for interrupting. Andrew and I did a comparison of a bunch of the different air source heat pumps that are on the market. Are you able to provide us with a curve for your heat production and COP against outdoor temperature?
There's actually a curve. We don't usually present it as a curve because there are detailed performance tables in the manual, and I'll show you where to find that as well. But there's actually a curve in this presentation just to see how the capacity and COP vary with outdoor temperature.
Oh, excellent!
So
Thank
we'll
you.
get there in a few minutes. Yeah, no problem. But any air source heat pump will have that characteristic. It's just harder physically harder to extract heat from cold air than from warm air, and that's why geothermal heat pumps have an advantage, because the ground outside that you're extracting heat from is the same temperature all the time, rather than being colder when your heat load is the greatest.
Yeah, it's just like, Kara and I've had the debates or discussions about this, like where's the sweet spot of what capacity, what percentage of the peak load do you cover from your heat pump versus supplemental, right? Because obviously
it's a bigger
right.
question with air source for sure. With geothermal, there's nearly not too much reason not to try to cover the coldest day heat load with the heat pump. I know that 75% or 70% is a common number, but we recommend that people seem to be happier if their backup heat isn't running, kind of thing, when it doesn't have to be. You don't have much choice with an air source heat pump, because you could try to size an air source heat pump for the whole load on the coldest day, but then when it gets warm out, the heat pump's going to have an enormous capacity at a very good COP, but it'll only run for 2 minutes because the heat load is hardly anything. So it'll be cycling on and off all the time in warmer weather. So sizing an air source heat pump will always be a compromise between too much cycling in warm weather and covering as much of the coldest day heat load as possible.
Yeah, and it is a challenge because, especially in a colder environment where, especially if you want to do all electric, and then you're like, well, I've got electric backup. You got the extra electrical capacity. You basically, you kind of have to size it so you have like it's 100% electric resistance that's covering the load, right?
Yeah, for sure. Yeah. So, yeah, if you wanted to compare, I don't know if you're interested in geothermal at all, actually, but it would depend where I lived. Like, I would go for I wouldn't be hesitant to install an air source heat pump if I lived in, Eastern Canada, where, the typical winter day is -4, -5 Celsius, that kind of thing. If I lived on the prairies, where it's always, it's routinely like very cold, like -20, -30, even -40, then an air source heat pump wouldn't be a good fit for there, in my opinion. And when you go further west, or if you go down into the more southern states, or to BC, then it becomes a very reasonable thing to install again. It's not that it doesn't work in colder places; it's just that it would require that much more backup heat, and the capacity would be that much more reduced. It would spend more time running at its minimum temperature. These units run the compressor down to as cold as -22 Celsius outside. So that's below that temperature, your backup heat needs to take over the whole load. So with an air source heat pump, you have to size the auxiliary heat, or the backup heat, for the coldest day heat load, because even if it rarely ever gets there, you have to have that possibility covered. And I think you guys are mostly in Ontario. I know it can get fairly cold in southern Ontario there too. You would have days when the heat pump can't run because it's colder than -22 Celsius outside. So
yeah, actually, it's pretty close. The 10-year return for Toronto is -25.6 C. So
okay,
we have to install the backup, but we don't have to turn it on very much.
Okay, that's with air source heat pumps, or?
With air source heat pumps. I just had an energy modeler come back and tell me for the new climate data, the current climate weather file, our backup actually didn't turn on.
Okay.
Because the building kind of surfed over those worst case hours.
Okay.
Yeah,
enough
it was interesting.
thermal mass in the building, kind of thing.
And we were. That's it. We were using a larger air mech unit for that. It's like a great big office building. To hit TGS Tier 4 here in Toronto for your. I don't know if you know this, but we basically need heat pumps now.
You do what, heat pumps? Sorry.
We basically need heat pumps. There's really very few other ways to hit the step code change that we hit in May.
Yeah.
So even
a lot of jurisdictions are going that way. I mean, there are big big programs to like, say, New York State, to say no more fossil fuel domestic water heating, which is huge, right?
Yeah.
Huge heat pumps, but I think they're going to have trouble finding enough heat pumps. Or to have
that is
heat pumps.
Definitely why we're having this meeting. The availability of heat pumps on the market is, at all size ranges, pretty limited, especially if you, for whatever reason, geo isn't the thing for your project.
Well, air source is much easier to install for sure. It's just having, I think people are happy with air source heat pumps because they work very well. but not if they've been given unreasonable expectations. You know, like some installers have said, these things are just as good as geothermal heat pumps, and your power bill will only be $50 a month and that sort of thing. And that's, at least with a traditional house, that's not the case. So having reasonable expectations is key with air source heat pumps, I think.
Right, and when you're talking about a passive house, in a perfect world, we see fairly low loads anyway. So we do. If you invest in geo, you maybe don't save as much as you're hoping because you weren't generating as much heat as you thought you'd need anyway.
I can see that. Yeah, I mean it's the same kind of situation as if you get a geothermal heat pump before you upgrade your windows. There's no reason to upgrade your windows anymore because the payback on the windows just went down by a factor of 4, or I mean the payback time went up by a factor of 4. So
well, that's right. And if you'd done it in the opposite order, you could have bought a smaller heat pump.
Yeah, exactly. So before I forget, in regard to passive houses, we started to produce, we haven't sold a lot of them yet, but specifically because I got some requests from passive house builders, we have very small water-to-water heat pumps that I don't think you can get anywhere else. So we have water-to-water heat pumps in sizes from 1 to 1.5 tons. So something to keep in mind. I can tell you about that some other time. Just thought I'd mention it before I forgot. All right, so let's take a look at some more slides. So of course, these are just some general points that were in the presentation. COP can be very high, actually, if it's not very cold out, up to 4 or 5, even 6, because it's easy to extract heat from warmer outdoor air in the spring or fall. As I mentioned, the minimum outdoor operating temperature, minus 22 Celsius. All the important stuff, we already talked about that. All the important stuff is inside. And there's a built-in control board as standard equipment that has all kinds of cool features. It has data logging, and actually I'll show you more about that in a second, but it does have BACnet as well. So if you're ever doing a commercial project with a building control system, the communication ability is built in.
And will it, one of the things we want to collect more data on for passive is its loads, actual heating, cooling loads.
Mm-hmm.
So can we collect from this the essentially the heating or cooling output of the unit?
Yes, you can gather all the operating data is available through BACnet, and to get the actual capacity, you would need to add a flow meter because there's no flow meter built in. So you need there are built-in temperature sensors to see what your temperature difference through the heat pump is, but it doesn't measure flow as standard equipment. So you need to add a flow meter and do the calculation in your controller. And you also, if you wanted to calculate COP, you would have to also have a there is an available current sensor, but there's no power sensor. Because it sounds like you'd always have the same voltage, and a current sensor would get you most of the way there, and that's true. But to actually measure COP, you would need like a power transducer that would measure the voltage and the current and convert that to watts used. So those are the things that's missing to do calculations of capacity and COP.
In a non-BACnet environment, can you get to the data?
The data is available all the time. So if you hooked up a BACnet capable controller, you could read these. You could read whatever data that the heat pump has from the BACnet system. Yeah.
So you have to go through BACnet.
To monitor in real time, you do. You could also have a laptop hooked up. There's a USB port on the board, and we have a PC app that's free on our website, and you can monitor anything through there. But there'd be no way to, no way that I know of to get the data in real time into another system, other than through BACnet.
Okay. Any plan to support KNX?
Support what, sir?
KNX.
KMX?
KNX, yeah.
Oh,
different.
it doesn't sound familiar, so there must not be.
Okay.
Yeah.
Yep. Thanks.
Yeah, there is a Modbus capability on the board, but that isn't implemented except on a few models of heat pump where it runs a thermostat or something like that. So it's a Modbus capable board, but we don't have any Modbus protocol that the customer can use to the interface. It's almost like Modbus is almost the same as BACnet anyway, with just a different layer on top of it. So
yeah,
BACnet's probably the way to go. or it's definitely the way to go. All right.
Thanks.
So some other features here. The outdoor unit only has a fan and air coil. It actually has the refrigerant expansion valve in the for heating mode in the outdoor unit, and there's an outdoor temperature sensor, so the unit always knows the outdoor temperature. The fan motor is it's fully variable speed, and the speed is controlled by a PWM signal from the indoor microprocessor board. The air coil is E-coated, so it's more robust. If it's installed by the sea, it should never corrode and wear out. When I was looking at air source heat pumps when I was designing these units, I found it was very hard to get into any kind of air source heat pump. Like, you had to be kind of have a big manual and be a intrepid mechanic to get the unit apart to see what was inside. So in this case, it's very easy to get at. The whole fan panel is hinged and swings out of the way with 2 bolts. So you can see that here. So very easy to open and inspect if you think you have an icing problem or something like that, which hasn't turned out to be a thing, but very easy access for components and to inspect the air coil, maybe to make sure that there's no leaves stuck in it or something like this. You've probably noticed that on a previous picture there was a 4-fan outdoor unit. So the smaller model sizes have a single fan, like is pictured here, and that would be the ATW 25, 45, and 55. And then the 2 largest model sizes, 65 and 75, have that 4-fan unit that you see there. Just a appearance difference. All right, so yeah, when we were designing these units, I mentioned we were trying to overcome some of the problems that we heard from air source installers, and one problem that was being experienced in the field was that usually there's a condensate tray under the air coil, and the condensate after defrost, because every air source heat pump needs to defrost due to the humidity in the air, the defrost condensate would refreeze in the tray, and the bottom of the air coil, first the fins would disintegrate, and then the ice would attack the tubing. It was very hard not to get that condensate refrozen in the drip tray. So we made the design. We eventually came up with the design that the air coil is on a 15-degree angle. So any moisture which is running down the outside of the coil during defrost just runs down to a single point. I'm not sure if you can see my mouse pointer, but if it runs off to a single point, it can't really be retained there by the surface tension of the fins, and it'll drip straight off. So there's nothing there to refreeze, and there's also no bottom tray. So one thing to be aware of when installing these is you shouldn't install it on somebody's front walk, because there will always be moisture coming off the coil in the winter. But as a result, we haven't had any air coil degradation issues over the 7 or 8 years that these have been in operation. So it's been very successful that way. And there's a good intelligent defrost logic. I mean, the old school way of controlling defrost was just to have it on a timer. I don't think anybody actually does that anymore, but ours runs on the suction pressure versus the outdoor temperature. So we know what the refrigerant suction pressure should be according to the outdoor temperature with a clear coil. And then if the suction pressure falls below that, the controller knows it's time for defrost and initiates a defrost cycle. And of course, you'll see the most. Sorry, go ahead.
I didn't mean to interrupt. Just what you can finish, and then okay. Just wondering, because it's dripping water. I don't know what volume of water it'll be, but is there a minimum? Obviously, you want to keep it like above the snow line, but is there a minimum height above grade or above? Because it could also be installed on roofs. Like what's?
Yeah.
So Andrew,
you want to keep the level. You want to keep the unit both above the snow level and above the level of the accumulated ice under the unit, which in practice doesn't accumulate very high. But
I was going to say here in southwestern Ontario in Toronto, one of the speakers at the ASHRAE conference this year was like, just for goodness sakes, he'd trace your drains under your units if they're on the roof, because they had issues with enough snow and ice accumulating that it posed a structural concern.
Oh, really?
Under larger arrays, right? If you got 10 of them up there, it's a much bigger deal.
Units, you would get a big ice buildup under them. Like, I don't think these are of the size where that would be a trouble, but I guess if you put 10 of them, it might be an issue. So good thing to keep in mind. That's true. We have usually we sell these with accessory leg kits, so that's one of the things that most people order. And we have a 15-inch leg kit as well as a 30-inch leg kit. I think most people get the 15-inch leg kit, but there's the 30 in case you're installing it in some very snowy location, and you always want to make sure that the outdoor unit is above that. Was that the question? I can't remember.
Yeah.
Yeah.
Thank you.
So yeah, you want to make sure it's probably not a good idea in Canada or in any snowy location to just install the unit on the ground. So you should use some kind of either, the accessory leg kits we have, or you could put it on ankle brackets like you see mini split heat pumps installed on all the time. That'd be totally feasible. It's just not a very heavy unit, right? There's not even a compressor in it. It's maybe a little larger than a mini split heat pump, because mini splits are usually like a ton or a ton and a half kind of thing in capacity. But yeah, totally doable on building brackets. There's an LCD interface right on the indoor unit for, it displays it cycles through the different operating data points. And there's also an interface there to make settings, and the most common settings anyway, in the control board. It's a really good idea to have a laptop, just any old Windows laptop or a new one, of course, with our free software on it and a USB cord. And that USB cord comes with the unit, as well as a USB with the manual on it. But that allows the installer or whoever, even the homeowner, to see the full capabilities of the control board and monitor different things, make all the settings, adjust all the settings that are adjustable, kind of thing. Although it is possible to do the most common settings through this little LCD screen. There's onboard water temperature control logic. So the heat pump, without any external thermostat or aquastat, has the ability to monitor the buffer tank temperature and maintain it to a user selectable set point temperature. And you would, of course, choose different water temperatures depending on what your hydronic distribution system was. So there's built-in temperature sensors, and the way that the heat pump monitors the buffer tank temperature is to turn on it has control of the indoor circulator. So it starts the circulator every 6 minutes for 2 minutes. And at the end of that 2 minutes, if the water temperature is shown to be below the set point, then it starts the compressor and heats the water. So it's easy to install that way. You don't have to install any aquastat. You can put an external temperature probe on it instead of using the temperature probes that are built into the unit. If somebody doesn't like the idea of the circ pump coming on every 8 minutes, so 6 minutes off, 2 minutes on. But most people find that feature to be one that they use and one they like the sound of. There's an outdoor reset function too. So of course the air source heat pump always knows what temperature it is outside, and it can reduce the buffer tank temperature on warm days when your heating distribution system doesn't require such a high water temperature. So that's a good energy saving feature, because of course the lower the heated water temperature you can use, the higher the COP is, and the higher the capacity is in watts. So three-way access valves, you'll notice them here. They're just like on a mini split. So one of the disadvantages, I guess, of not having a monoblock system like our competitors is that refrigeration work needs to be done on site. But it's a very common expertise. There are a lot of people around, or service technicians around, who know how to install mini splits, because there are so many mini splits put in every day that the same expertise is used to connect the indoor and outdoor units in this case. So there's a three-way access valve there, which allows you to, once you have your tubing connected and vacuumed, you just open up this valve to let the refrigerant from the indoor unit into the outdoor unit. And then you might, if you have a long line set, there's a chart in the manual with how much refrigerant to add. So a very common way to connect the indoor and outdoor units together. Here's the control board that I was talking about. We use this control board in our air source, and also actually most of our other heat pumps. The only heat pump we don't have it in yet is our water to air heat pumps, like geothermals, because they're not very complex, and this board, of course, adds some cost. But it's a nice board. We developed it ourselves. It has the BACnet interface I was talking about. It has a USB port for connecting your Windows laptop. It has that built-in aquastat function to control the buffer tank temperature, and the outdoor reset function built into it. There's digital display of all refrigerant and water loop, like water line in and out temperatures, and also refrigerant pressures. So service, anybody familiar with refrigeration will find that cool. You don't need to hook up your gauges anymore to see what the refrigerant pressures are doing. It's all at your fingertips there with this board. For data monitoring, it has a data logging feature. So whenever the heat pump is on, it's always recording all the operating data up to, I think, 42,000 points. So that's something like 30 days or 27 days or something at the default logging rate. And while you have a laptop hooked up, you can also graph all those things. So there are different graphs you can monitor in real time. And there's a spare user configurable analog inputs for, so say, connecting a power meter. If you wanted to hook that up and monitor that through the BACnet system, say, that would be something you could do.
I have a question here about this USB interface. Can you do some settings with this interface or just the graphs?
Can you do what with it? Sorry.
Just observe the graphs, or
yeah,
you can also have some setting adjusted from this interface.
Yeah, the graphs are just visible on the connected laptop. So I don't think you could graph things that were being reported in the BACnet system, but not through our PC app. The PC app would just be on the connected computer.
So no, you cannot adjust anything there with the USB interface.
The USB interface was just for it's for using our PC app, which can do the adjusting of parameters, changing the configuration settings, graphing. You can download. It's also for downloading the data logs. So if you had a problem with the heat pump or the connected hydronic system, you could go and download the data log that's already stored in the control board. So you would use that USB jack for that.
Thank you.
And something else too that I was going to say, but I can't remember. Right. So there's this is just a note about the PC app. So it comes on a USB stick with the unit along with a USB cord. It's also on our website. So that's the other thing you can do with the laptop and the USB port is upgrade the firmware. So if there's some improvement we make to the like bring out a new feature like radiant cooling dew point calculation, which we might do in the future, that would be you could just upgrade the firmware to take advantage of those new features. Or if there's some problem with the way that the heat pump is running, you can often fix it through firmware. This isn't such an issue now, but it was we were making quite a few improvements when these units first came out, so it was very easy for the users to just upload the latest firmware and have those logical improvements, like say the way the defrost particulars of the way the defrost cycle worked and that sort of thing. So you can do that as well through this PC app. So for performance, there are one thing you can look at in there's a manual on the website that includes specifications. So that's the best place to look for the performance of all the different models. The simplest performance chart to look at are the standard capacity ratings, and there's actually no AHRI standard for air-to-water heat pumps in heating mode yet. But when they update their standards, it's very likely that these temperatures will be used as the standard temperatures because they're from other standards like water-to-water heat pumps or air-to-air heat pumps. So these are some standard conditions, and it shows the output and the COP at two different indoor water temperatures, 105 and 120. And for each of those, there's two outdoor temperatures, which are standard rating conditions. So this table is available. And there's also a more, I don't have a picture of it here, but there's a detailed performance table with many more outdoor temperatures on it. So you can, if you're curious about how much was this heat pump going to put out when it's this temperature outside, you can look at those tables, and they're, as I say, they're in the manuals. As far as a curve goes, this kind of shows how the COP and the capacity vary with the outdoor temperature. If I have I apologize. I used to have a Celsius one in there, but I'm used to thinking in Fahrenheit, and so are our American customers. But so this one is the imperial version. You can see as the outdoor temperature This is pretty close to the coldest temperature here. It actually goes down to -7, but at -5, you're going to have a COP of about 1.5. And as you go up to, say, a 65-degree outdoor temperature, that can go as high as 5.5. So there's a characteristic curve of how that varies, and same with the capacity. So for an ATW 75, which is the largest, the 5-ton model size, you can see at a very warm outdoor temperature, you can have a heating capacity of around 70,000 BTU per hour, which is probably 5.8 tons or something like that. And at the coldest outdoor temperature that the heat pump operates at, you're down to about, what is that, 26,000 BTU per hour or something like that. So it does vary quite a bit, and that's where the need for auxiliary heat comes from, at least in a typical house at colder outdoor temperatures. You might have the heat pump. One suggested sizing method is that you try to cover the load when it's around freezing outside with the heat pump. So in this case, that would be about, looks like about 50,000 BTU per hour. But as I say, it's always going to be a bit of a compromise between covering as much heat load as you can on a cold day and having it cycle too much in warm weather. So not a very exact science, actually, sizing the air-to-water heat pump. So here's what this is a slide I just added today because for some reason I didn't have it in previous presentations, but this is if you had a system installed, this is what it might look like. So the indoor unit of the heat pump is here. You can see it's connected with refrigeration tubing through the outside wall to the outdoor unit. And that's the back of the outdoor unit since the fans are facing away from the house. The maximum line set length is 70 feet, so you have to plan a location where that makes that possible, kind of thing. The heat pump, the actually indoor unit comes charged with enough refrigerant for 20 feet of line set. So if you have more than that, you can add a little bit of refrigerant to it to make up for that longer line set. Of course, the main job of the heat pump is going to be to heat or chill a buffer tank. There can be 2 buffer tanks, as I mentioned, and there's it can automatically switch back and forth to heat a hot tank and chill a chilled tank. This is most people just have 1 buffer tank and do a seasonal switchover. So this is these are the main outputs. The water lines from the heat pump are these 1-inch lines here, connected to the buffer tank. We actually sell buffer tanks that are made by a Quebec company, Thermo 2000. So they call them alt-source tanks. But you could use any kind of tank which has suitable elements for backup and is a suitable size. So for an ATW 75, we would suggest a 70-gallon tank, and we also carry a 50-gallon tank for smaller model sizes of ATW. If you're going as small as a 25, you could even use a smaller tank. You could use maybe a 40-gallon buffer tank. So that's fairly flexible. But of course, the bigger the buffer tank, the less cycling the heat pump is going to do, the less turning on and off, and the more thermal storage you have. So big buffer tanks are a good feature. And then your heating and cooling zones, of course, instead of talking to the heat pump, they're going to be either opening a zone valve and or starting a zone circulation pump, which is going to demand water from that buffer tank. On the other side here, we have the domestic tanks we were talking about earlier. So the desuperheater, these small connections, 1/2-inch connections on top. And it's that desuperheater is heating a domestic water preheat tank, which can just be a normal water tank, an inexpensive water tank without the electric elements connected. And then in the case that, that's not, it doesn't heat the water all the way, there's a final water heater, which is usually an electric tank, or it can also be an instantaneous tank of some sort. So this diagram is also in the manual. There's no need to look at that in too much detail, and it's in the piping chapter. So and there's also in the manual is a bill of materials, because the common question is like, what can I get from you guys? Like, you guys are the heat pump manufacturer, so what will we need to get from you, and what will we need to get from elsewhere? So this sample bill of materials is also in the manual. We're the manufacturer of the heat pump, so of course we'll sell the heat pump, the indoor and outdoor units, which comes with shielded 18/8 wire to go between the indoor and outdoor units. And we also sell accessory buffer tanks because they can be hard to find from, just from the wholesaler down the street, at least in a certified space heating large element kind of variety. And then there's a list of other things that you'll need from other places for a typical installation. Just a note I put in here about certification marks. You'll often see CSA or UL or ETL stamped on for a product safety certification. TUV is the one you'll see on our equipment because that's the agency that we've contracted to do that certification, but it's entirely equivalent to CSA or UL or ETL or probably a few others like QPS or something like that. So that's a common question you get. Why isn't the CSA certified? Well, it's any agency certified by OSHA in the States can do these product safety certifications, and they're all equivalent. So if you get that question, you'll know the answer. Quite often, you'll see requirements, especially for grant programs, that something carry like a heat pump carry the AHRI certified mark, or the Energy Star, which is a benchmark. It's basically the same group of equipment. For air-to-water heat pumps, as I mentioned before, there's no AHRI program for air-to-water heat pumps in heating mode. So you won't find these on ATWs, and it's not because the ATW doesn't qualify for AHRI or that we haven't bothered to certify it. It's that there's no program existing. So I'm sure that'll be changing, and when it does, we'll have that mark on there. The installation and service manual, it's actually an application manual as well, is kind of a one-stop place where you can get all the application information, how to install it, and also all the specifications in one document. And you can find this on our website. Of course, it also comes on a USB with the unit, but our website is nordicghp.com. I think it's maybe on the next slide. There we go. nordicghp.com. And then there's a product drop-down menu at the top left. You go to Nordic air source heat pumps and go to the product page. Another place to get all the manuals in one place is there's a for dealers tab right in parallel with this Nordic heat pumps tab. And under for dealers is download manuals. And then there's a list of all our manuals that you can download. A very easy place to find all the documentation. So yeah, this manual, if you have any questions, the answer is probably in there. We try to put as much information in there as we can so that, of course, we don't have to manually answer all questions, but also for, nothing's a secret. Everything's in this document. One thing I should mention too is that quite often cooling with an air-to-water heat pump is done through hydronic air handlers, and you can find on the market in-room kind of air handlers that accept chilled water and transfer that effect into the room, of course. So you mentioned AirMech, they do make such in-room air handlers, and there are some other manufacturers like Multi-Aqua and Polar, Soncor, HVAC. So we hope to get some of these on offer as well for accessories so that people can buy them from us, but we do manufacture ducted hydronic air handlers. So I just put this slide in here in case you're looking for it's kind of a larger ducted air handler. It's a nominal 5 tons in size, but we have 2-pipe, 4-pipe varieties, and also vertical and horizontal configurations. So that's something that you can find information on our website about as well. I think that brings the presentation to a close. So thanks for, I guess that was an hour long, so not too bad. It's kind of the maximum length for one of these webinars, but if anybody has any questions, I'd be happy to answer them.
I have another one, but
sure.
I tend to hog the questions, so I'll give space if anyone else.
Mm-hmm.
No questions from me.
No, I'm good.
All right.
Okay. Yeah, it's about chilled water temperatures. So what's the lowest the heat pump can go down to, and then I guess technically like what you could store it at? Like how low could you get the tank to?
I think a common temperature to use is 45 Fahrenheit. Sorry for the Fahrenheit again. I don't know what that is in Celsius, but I think it's 7 degrees actually. But you can go a little bit lower. If I open up the air-to-water manual here, which is the one I was just mentioning.
And that's actually, the output of the heat pump or the
max
storage?
Well, the specifications of the heat pump are for coldest leaving water temperature, and there's there's a min-max temperature table toward the end of the manual here. Let me just go to it. Operating temperature limits. So for cooling, we're saying that the minimum leaving water temperature is 41. So a reasonable minimum set point is probably 42, something like that. Yeah. So.
Okay. And then is there a kind of rule of thumb in terms of transferring it to the buffer tank, what you'd end up storing the tank at?
That's the there's a water temperature set points for the buffer tank are in the settings of the heat pump. So in the control board, it won't let you set the temperature lower than the heat pump can achieve. And I can't remember exactly what the limit on that is. I think the minimum might be, it's 40 to 42 anyway. I have to check on that, but the official specification here is that 41 is the minimum. So 40 would be a very reasonable setting. 42,
yeah, I just wanted, like, so you could get the tank to 42? I just figured there'd be like some heat exchange loss or something.
There would, yeah, and that's if you put antifreeze in, you could actually go lower than that. But it's common practice not to put antifreeze in a hydronic system unless you're expecting to heat a garage floor that's freezing some of the time or something. Or if another legitimate use for antifreeze would be if you want to do lower temperature cooling.
Yeah, you're getting into what I'm thinking.
Right. What kind of temperature were you aiming for?
I don't know. These are ongoing discussions for Kara. Basically, I want to try to do cold air distribution. So ASHRAE actually has a guide they published in the 90s about cold air distribution, which I understand is done more in industrial buildings.
Okay.
Not so much like residential or commercial, but I want to see if we can
gain
extra cooling capacity out of our ventilation air. So essentially a strategy in passive house you may be aware of is that you can heat via the air if you design it right. But cooling via the air is solely via the ventilation air is challenging.
Because there's not enough airflow there. Yeah, I understand.
Yeah, exactly.
Yeah, so actually it says right below that in this table that you can go down to as low as 32 if you have antifreeze. So it's right there on the next one.
Okay.
Yeah. Now that doesn't come up very often, so that's why it wasn't right at the tip of my at the top of my head. But yeah, you can get down there if you have antifreeze in your system. So that's a good strategy. Actually, you'll get very good dehumidification if you have such cold water. Your COP won't be quite as high because you're going for a bigger spread between the outdoor air temperature and the temperature you're chilling to, right? But in general, it's not as big as in heating mode anyway. So unless it's
the hit, right?
degrees outside, if it's the end of days or something.
Well, that's it. Well, I'm not looking at doing something in Georgia, but in Southern Ontario, we've got this this peak cooling low that happens, for 2 weeks a year or whatever the period is. It gets hot and humid. Can we cut that down enough to comfortable temperatures without having to put all the cooling in?
That's it. Yeah. So you can use those temperatures. You could use that 32 there and as a theoretical minimum, and I'd aim for a little bit higher than that, but it's certainly possible to get down there.
Okay, and you would do the antifreeze would be in the entire water system, like in the tank, and
have to be all the water that's in the buffer tank. So that's the water that's circulating through the heat pump and also through the distribution system would have to have antifreeze in it. Yeah.
Oh, right. So that's interesting because you like why? I mean, why would you, like, if you wanted to go instead of at 7 degrees, you wanted to go down to 4 degrees or 3 degrees? Like, is it just because you could have temperature differentials where some areas could freeze, or?
Oh, definitely. Yeah, it's to avoid freezing for sure. Because the temperature inside the heat pump, a heat exchanger, is much lower than the water temperature that's coming out of the heat pump. So the place it's going to freeze is inside the heat exchanger of the heat pump. And there's coaxial heat exchangers used on this heat pump. So even if you freeze them, it's not the end of the world. Like they probably won't break, but if a heat exchanger breaks, the heat pump is ruined. So that's the goal of heat pumps, is to not freeze the heat exchangers.
But what,
Uh,
if you, so because you've got water coming from the indoor unit to the buffer tank, right? Like that, there's a loop there, or is that a closed loop, or is it?
It's all a closed loop. Yeah, the hydronic system is all a closed loop. It's just that one part of it is the loop between the heat pump and the buffer tank.
Yeah,
And
so couldn't you just put antifreeze in that loop and then the buffer tank itself not have antifreeze?
Well, there wouldn't be any. There's no hydraulic isolation between the two things. So
No, that's okay. That's it. It's one closed loop. There's not there's no separation of the
Right.
water streams. Okay.
Yeah, there's not like a heat exchanger in the buffer tank and it's exchanging like one loop exchanging heat with the other. It's all
Gotcha.
the same. Yeah, it's just
Okay.
a big empty tank. Like there's nothing inside it. If you
And
were
so-
to use a tank with a coil, you could have antifreeze in part of it, but temperature approach. So you'd have inefficiency introduced by the temperature approach between the two loops. And there are applications where you want loops to be isolated like that, like if you're heating pool water or if you're a fish farm or something, and you have to use a secondary heat exchanger that's cleanable. So there's lots of different reasons that you would have such a water-to-water heat exchanger or an indirect tank, but you wouldn't normally do that in a house because you would introduce that efficiency loss of the temperature approach between the two in the water-to-water heat exchanger kind of thing, and also an equipment cost, I guess. Yeah.
So there's no issue with having antifreeze in the system like in heating mode then?
No. I mean,
Okay.
any antifreeze has a little bit less heat transfer capacity than water, but unless you get up to higher concentrations of like propylene glycol, which you might actually be doing if propylene glycol is a non-toxic antifreeze, and it's the most common one used these days because it's not poisonous and it doesn't, it's just the same thing which is an ice cream, so it's not very dangerous. But that particular, as opposed to methanol or ethanol, propylene glycol is harder to pump and has a noticeably or a significantly less heat transfer capacity than water. So it does introduce a bit of a disadvantage if you have to use a high concentration of propylene glycol.
Okay, yeah, I guess that's something we could work out in more detail because that would obviously
That's
affect
easy to look up,
potentially pumping power through the distribution system, right?
And a little bit of loss on the
So actually,
on side because it has a lower heat transfer coefficient. It's like 0.95 or something like that.
would that also affect if you had a coil on the delivery side, like in a room, you would also have less heat transfer there?
You would, but
Right,
I don't know
okay.
if it would be a deal breaker. I mean,
Right,
it's commonly used in geothermal systems, and those are still used. So, yeah, it's just methanol was a very good antifreeze. It's just that you needed less of it too, and it was very viscous. Not viscous, unlike propylene glycol, which has a significant viscosity. So it was easy to pump, and it had a good heat transfer capacity. But unfortunately, it's not non-toxic. So that's a requirement in many places. Although if you have a jurisdiction where it's allowed, you could use methanol as well. Actually.
Okay. All right. Great. Thank you.
Yeah, no problem. Any other questions?
I think I'm done.
All right. So yeah, I don't know if my contact information was on this slide or not. I guess not. Anyway, our website is nordicghp.com, and all of us, like Dan, Chris, and Susan, I'm Dan, our email addresses are our first name at nordicghp.com. So actually the telephone number here for tech support is also available, and or you can email me, Dan at nordicghp.com, and I can answer any questions you think of afterwards.
Yeah, awesome. Well, yeah, this has been really informative. Appreciate you, Dan,
great.
taking the time to meet with us.
Yeah, no problem.